2022 AP Calculus AB free response question number 6. Particle P moves along the x-axis such that for time t is greater than 0, its position is given by x sub p of t is equal to 6 minus 4 times e to the negative t. Particle Q moves along the y-axis such that for time t greater than 0, its velocity is given by v of sub q of t is equal to 1 over t squared. At time t equals 1, the position of particle Q is y, q of 1 is equal to 2. So part A through D are displayed here. You can pause the video, read through them, try this on your own, but in the upcoming slides, we'll take a look at each part on an individual slide. So let's begin. Part A, find Vp of t, the velocity of particle P at time t. So we know the velocity is the rate of change of position, and we're given a position function for P. So we know that x sub p of t is equal to 6 minus 4e to the negative t. We're aware that Vp of t is equal to the derivative of that position function, which is going to be, well, the derivative of 6 is 0, and when I differentiate negative 4e to the negative t, chain rule there, make sure you realize that that exponential is composed with negative t. So we're going to do the derivative of e to the x is itself, but times the derivative of the inner function, which is negative 1. So fully simplified, we're going to get 4e to the negative t, and that's our velocity function for particle P at any time t. And there's part A. That's all there is to it. Now let's look at part B. Find the acceleration of particle Q at time t, and then find all times t for t greater than 0 when the speed of the particle Q is decreasing, and justify your answer. So we got about 3 parts here. First, we're going to find the acceleration function. Then we're going to determine the times when the speed is decreasing, and then we need a justification. So the acceleration of particle Q, we know is the derivative, the rate of change of the rate of change. We're given a velocity function, which represents our rate of change of the position of Q. So we just have to differentiate that to get our acceleration function. So when we go to differentiate 1 over t squared, which is what we have here, I'm going to reformat that as t to the negative 2, because once again, that I've stated in previous videos related to this 2022 exam, anytime, or just in general when we're working with derivatives and integrals, anytime we can reformat functions as power functions, everything's way easier. So now that I have it as t to the negative 2, I can just use my power rule, multiply the leading coefficient constant by the current exponent. So negative 2 times 1 is negative 2. And then we subtract 1 from our exponent to get negative 3. If we want to reformat this to negative 2 over t to the third, there's our acceleration function. So part 1 of this question is now taken care of. So we have an acceleration function, and now we need to know all times t when the speed of the particle is decreasing. So how do we know when a speed is decreasing? Speed being the absolute value of velocity. So imagine we have some velocity. If the velocity is constant, not changing, then our speed is constant. So how do we know when we're going to be decreasing speed? It's when we start to decelerate, and we will decelerate whenever acceleration and velocity have opposite signs, because not only do they represent a magnitude, but they also represent a direction. Therefore, they're vector quantities. So the signs tell you direction. Now that we know that, if velocity and acceleration are going in opposite directions, you have a deceleration indicating your speed is decreasing. So now when we look at our velocity function, 1 over t squared, and we look at our acceleration function, we're only considering when t is greater than 0. When t is a positive number, this velocity function is always going to be positive. When we have t to the third, whenever t is positive, this acceleration function is always going to be negative. So we have just determined that this particle is always going to be decreasing its speed 4 times t greater than 0. And our justification is going to be explained through the relationship between velocity and acceleration. So we're going to say for all times t is greater than 0, the speed of q is decreasing because the velocity is greater than 0 and the acceleration is less than 0. So we've given a justification. The velocity and acceleration are opposite signs, therefore indicating our speed is decreasing. And we also found the acceleration function at the start. So we have answered all three parts of this question. So now on to part C. Find the position of Q at time t. Okay, so the position is going to be found by integrating the velocity. So yq of t is going to be found by integrating vq of t dt. So vq is 1 over t squared dt. Reformat as a power function again, t to the negative 2 dt. So we're going to reverse that power rule. So before, when we differentiated, you would multiply the front by the exponent and subtract 1. So now we're going to add 1, and we're going to divide by that new exponent. So we're going to get to negative 1, and then we're going to divide by negative 1, which is the same thing as multiplying by negative 1. So we're going to get this. We're going to input our constant of integration. So this is what our position function is as a general solution, but we want a particular solution here because we're given this initial condition along with it to allow us to find that constant of integration c. We know that when we plug in 1, it should equal 2. So this is the same thing as 1 over t, by the way, so I'm just going to put in a 1 there now. So we're just going to be adding 1, and we'll find out c is 3. So now we can get our general or particular solution, which is negative 1 over t plus 3. So there's our position equation for particle q, and that's all that we had to do. So we use that velocity function, knowing that velocity is the derivative of position. To find position, I can integrate the velocity function. We're given an initial condition, which allows us to find that constant of integration c. How did I compute the integral or find the antiderivative? Once again, reformatting as a power function is the easiest pathway. And that is all there is to part C. So let's jump to part D. As t approaches infinity, which particle will eventually be further from the origin? Give a reason for your answer. Okay. So this is, so farther from the origin, this is indicating we're going to have to analyze position. So our position for particle P we have given to us. And in part C, we just found the position for Q. So here are our two position functions. P is moving along the x-axis, y is moving along the y-axis, or Q is moving along the y-axis. So let's see which one's going to be farther from the origin as we approach infinity. This is essentially a limit question. Okay, so we're going to say, what is the limit of this position of P as t approaches infinity? Well, as this first function approaches infinity, we have 6 minus, and I can rewrite it like this. This may be helpful in the evaluation. So as this t value goes to infinity, the denominator of this fraction is growing without bound. So the overall value of that fraction or that ratio is going towards 0. Right, so a limit evaluation here. So that fraction part is going to 0. 6 minus 0 is 6. So we found out that that's 6. So as t approaches infinity, the position of the particle in relation to the origin is approaching 6. Now let's do the same limit evaluation for particle Q. So as t approaches infinity, we're going to have to analyze this function here. So as t goes to infinity, once again, this ratio is going to 0 because 1 over a number that's growing without bound, the overall value is dwindling to nothing. So 0 plus 3 is 3. So as we can see, to answer this question, we now have an answer for which one is going to be farther from the origin. That is going to be particle P. And I'll put it in red since that's the actual answer. And for reasoning, well, you can show that limit evaluation. You can say, well, as the positions of these particles approach infinity, we see that one approaches 6 and one approaches 3. So you can analyze those functions and show the math and give some justifications like I did verbally for this blue function off to the left and the one that I've written in red up in the top right. So that's all there is to part D, and that is the full question number 6 for 2022 AP Calculus AB free response question.